Classical mechanics versus quantum mechanics, contrasting theories in physics. Classical mechanics and quantum mechanics are two fundamental theories in physics that describe the behavior of objects at different scales, from macroscopic to microscopic levels. They represent distinct approaches to understanding the fundamental laws governing the universe. 1. Classical mechanics overview. Classical mechanics, also known as Newtonian mechanics, is the branch of physics that describes the motion of objects using Newton's laws of motion and the law of universal gravitation. It applies to objects with macroscopic scales, moving at speeds much slower than the speed of light. 2. Scope. Classical mechanics provides accurate predictions for most everyday phenomena, such as the motion of planets, projectiles, and mechanical systems like pendulums and gears. It relies on deterministic principles, where the state of a system at one time determines its state at any future time. 3. Principles. Key principles of classical mechanics include Newton's three laws of motion, which describe how forces affect the motion of objects, and conservation laws such as conservation of energy and momentum. 4. Quantum mechanics overview. Quantum mechanics is the branch of physics that describes the behavior of particles at atomic and subatomic scales. It introduces probabilistic principles and wave-particle duality, challenging classical notions of determinism and predictability. 5. Scope. Quantum mechanics governs the behavior of particles such as electrons, photons, and atoms. It is essential for understanding phenomena like atomic structure, molecular bonding, and the behavior of particles in quantum systems. 6. Principles. Key principles of quantum mechanics include the uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. Quantum mechanics also introduces wave functions to describe the probabilistic behavior of particles. 7. Measurement. In quantum mechanics, measurements of properties like position or momentum yield probabilistic outcomes described by wave functions. This contrasts with classical mechanics, where measurements are deterministic and exact. 8. Applications. Classical mechanics finds applications in engineering, astronomy, and everyday technologies like vehicles and machines. Quantum mechanics underpins technologies such as lasers, transistors, and quantum computing, revolutionizing fields like telecommunications and computing. Conclusion. Classical mechanics and quantum mechanics are foundational theories in physics that describe the behavior of objects at different scales. Classical mechanics applies to macroscopic objects and is based on deterministic principles like Newton's laws of motion. Quantum mechanics applies to microscopic particles and introduces probabilistic principles and wave-particle duality. Understanding the differences between classical mechanics and quantum mechanics is essential for exploring the fundamental laws of nature, advancing scientific research, and developing technologies that shape our modern world.